Welcome back to another explainer. Today, we're taking a deep dive into the invisible, mathematically precise mechanics of collisions. We are going to strip away all the chaos of real-world crashes and look at the absolute, unbreakable math that dictates how things move, crash, and fall. If you've ever looked at a car crash and wondered about the hidden physics governing that reality, well, you're in exactly the right place.
Okay, let's dive right into this with a pretty terrifying theoretical scenario. Imagine you're driving a car into a solid concrete wall. Now imagine that this wall doesn't yield, not even a fraction of a single millimeter. If you hit that completely immovable wall, the math tells us that the duration of your impact is exactly 0 seconds.
Section 1. The foundation. F equals ma. So, to understand why a 0-second impact is just so catastrophic, we have to look at the very foundation of physical movement. This is Newton's second law, expressed simply as F equals ma. Net force equals mass multiplied by acceleration. It's the absolute core formula we use to calculate the force of any impact. And the math here is relentless. The heavier the object, and the faster it accelerates, or in the case of a crash, decelerates, the exponentially greater the resulting force pushing back will be. It is a direct, inescapable, proportional relationship.
But wait, we actually need to pause for a second on that word acceleration. In everyday language, we just think of acceleration as hitting the gas pedal to speed up, right? But in physics, acceleration is any change in velocity divided by the specific time it took to make that change. That time component, the exact duration it takes to speed up or slow down, is the absolute key to understanding force.
Moving on to section 2, the absolute baseline, the 0-second impact. So let's test this foundational formula against the rawest mathematical form of a crash. We're setting the stage with an object, let's say a car, with a mass of exactly 2,000 kilograms. Notice the speed. It's traveling at 100 kilometers per hour, which gives us a velocity of 27.78 meters per second. And it is heading straight into an obstacle, a rigid, perfectly immovable concrete wall that will not absorb a single millimeter of the impact.
Now, what's really interesting about this is an observation from the source material. Because the obstacle doesn't change shape, the collision therefore occurs at infinite speed. Infinite speed sounds like total science fiction, doesn't it? But decoding the math, it makes total sense. Because the wall refuses to yield, the transition time from moving at 100 kilometers per hour to a dead stop is practically zero.
And here's where the math gets crazy. When you take your change in velocity and divide it by exactly 0 seconds, your deceleration mathematically becomes infinite. And if acceleration is infinite, our F equals ma formula dictates that the force pushing back is essentially infinite. It's the immovable object asserting total physical dominance, causing complete and absolute disintegration. Section 3, the energy of motion, defining kinetic energy. Let's shift gears a bit and focus on the actual energy our 2,000-kilogram vehicle is carrying into this crash. Because in physics, all that forward momentum cannot simply vanish into the void. This brings us to kinetic energy. Simply put, kinetic energy is the energy an object possesses strictly because it's in motion. It's calculated by taking the object's mass and its velocity. When that massive vehicle comes to a stop, all of that stored motion energy has to go somewhere. And honestly, the numbers here are staggering. Our specific 2,000-kilogram vehicle traveling at 27.78 meters per second carries roughly 771,730 joules of kinetic energy. Think of those 771,730 joules as a ledger. When the car crashes, the universe must mathematically balance that exact ledger down to the very final decimal. Section 4. Real-world collisions and the factor of time. Thankfully, perfect, mathematically immovable walls don't represent most of the real world. Compare these two realities. On one hand, the immovable wall gives us 0 seconds of duration and an infinite spike in force. But on the other hand, we introduce yielding, things that bend, buckle, and break. A crumpling metal vehicle extends the duration of the impact. Look at how this shakes out. By introducing just a tiny fraction of a second of crash time, the math completely shifts. We are mathematically saved from infinite force because we increase the denominator, the time, in our acceleration equation. Let's look at the source's second example to see this in action. Here we've got two heavy 2,000-kilogram objects colliding head-on at 100 kilometers per hour. But unlike the concrete wall, these are steel machines. The metal will fold. And folding takes time.
That folding metal actively increases the duration of the impact, keeping the force well out of the realm of infinity.
Section 5. The Law of Conservation of Energy. Balancing the books.
So the crucial point is this. Even though that extra crash time lowers the immediate force, those two vehicles are still carrying massive amounts of kinetic energy. According to the law of conservation of energy, that forward momentum cannot be destroyed. The universe must balance the books by transforming it into new forms. And energy is incredibly clever at finding an exit. Notice the 3 highly specific escape routes it takes during a yielding collision: thermal energy, acoustic energy, and elastic potential energy. Let's break these down.
The first escape route, heat. When a car chassis crushes inward, the steel beams aren't just politely folding, the molecular lattice of the metal is being violently sheared and scraped against itself. This tremendous mechanical friction converts motion directly into thermal energy. If you touched a crumpled fender immediately after a high-speed impact, the wreckage would literally be hot to the touch.
The second escape route is sound. We usually just think of a crash as being, well, loud, but sound is physical energy. A massive chunk of those 771,730 joules is spent violently punching the surrounding air molecules. The mechanical displacement creates deafening atmospheric pressure waves that radiate outward.
But the third form is perhaps the absolute most crucial for understanding structural damage: elastic potential energy. As objects deform, the kinetic energy freezes itself into the twisted, bent metal. That deformed metal acts exactly like a highly coiled spring, trapped under immense pressure. And this brilliantly illustrates the concept in an everyday scenario. Think about a baseball hitting a wooden bat. To our human perception, we just hear a crack and see a perfectly round, solid ball fly into the outfield. But if you watch it in ultra slow motion, the ball flattens out against the bat. It looks almost like a squished sponge. In that fraction of a second, the physical squishing captures the kinetic energy as elastic potential energy, and then violently releases it by snapping back to its round shape, launching the ball into the air.
Modern car manufacturers actually use this exact same physics to keep you alive. They engineer crumple zones into the front and rear of your vehicle. These zones are designed to act as a mechanical sponge, crushing like an accordion to soak up kinetic energy as elastic potential energy. But more importantly, this crushing deliberately increases the collision time. Stretching out the deceleration time lowers the A in our F equals ma formula, keeping the ultimate force low enough for the human body to actually survive the impact.
So we've seen how energy always finds an exit through heat, sound, and deformation. But I want to leave you with this final, provocative thought experiment. Imagine 2 absolutely indestructible objects colliding. Now place that collision inside a perfectly silent, frictionless vacuum in space. There's no air to carry a sound wave, there's no friction to generate heat, and neither object can deform even a single millimeter. All the mathematical escape routes are completely cut off. So where does the energy go? It's something for you to ponder. Until next time, keep questioning the invisible forces around you.